Hello everyone, and welcome to this lecture on setting up a deep learning workstation. In this session, we will cover the essential aspects you need to consider when preparing your environment for deep learning experiments. First, let's discuss Jupyter notebooks, which are the preferred way to run deep learning experiments. Jupyter notebooks are an open source web application that are fantastic for creating and sharing documents that contain live code, equations, visualizations, and narrative text. They are widely used because they allow for interactive development, letting you run code cells individually and see the output immediately. You can also keep your code and documentation in one place, combining code, markdown text, equations, and visualizations in a single document. Sharing your work is also very easy, promoting collaboration and reproducibility. While primarily used with Python, Jupyter supports many other languages. As an example, here is a simple Python code cell. We set the variable a to 10 and b to 20, then calculate their sum and print the result. The output shows the sum of a and b is 30. You can also use Markdown within the notebook to format your text and include mathematical equations using LaTeX syntax. Here is an example of the famous equation E equals mc squared, and a more complex one showing a partial derivative. Next, let's talk about getting Keras running. Keras is a high-level API for building and training deep learning models. It can run on top of different back-end engines like TensorFlow, Theano, or CNTK. There are two common ways to get Keras running, but one is much more recommended now. Option one is using TensorFlow with Keras. TensorFlow is an open source machine learning library developed by Google. Keras is integrated directly into TensorFlow as tf.keras. This is the recommended way to use Keras today. Here is an example code using tf.keras. We import TensorFlow and its Keras module. We generate some dummy data for a simple linear regression problem. We then build a simple sequential model with one dense layer. We compile the model using the atom optimizer and mean squared error loss. We train the model for 50 epochs and then plot the training loss. Finally, we make a prediction on new data, specifically when x equals 5. The output shows the prediction for x equals. Option 2, which is less common now, is using a standalone Keras installation. Before Keras was integrated into TensorFlow, you could install it as a standalone library and configure a backend like TensorFlow, Theano, or CNTK. This code snippet shows a typical Keras configuration file specifying the image data format, epsilon value, float type, and the backend, in this case, TensorFlow. This commented out code block shows how you would typically use a standalone Keras installation. You would import from keras.models and keras.layers. The rest of the code for building, compiling, and training the model would be similar to the tf.keras example. Now, let's consider running deep learning jobs in the cloud. This offers flexibility and scalability, but also comes with its own set of considerations. The pros include scalability, allowing you to easily scale your compute resources up or down. It can be cost-effective for intermittent use as you only pay for the resources you use. You get access to powerful hardware like the latest GPU without significant upfront investment, and cloud providers offer managed services that simplify development and deployment. The cons include potentially higher costs for continuous use compared to owning hardware. Data transfer can be time-consuming and costly for large data sets. There are security and privacy concerns when working with sensitive data in the cloud, and setting up and managing cloud environments can be complex. This conceptual code example shows how you might interact with a cloud machine learning library to submit a training job. It's important to note that the actual setup varies greatly depending on the cloud provider like AWS, GCP, or Azure, and the specific services used. The code outlines configuring a job with parameters like the machine type, accelerator config, specifying the GPU type and count, the location of your code package, the entry point of your training code, and command line arguments. Finally, let's address the question of what is the best GPU for deep learning. Choosing the best GPU depends on several factors: your budget, the type of deep learning tasks you'll be performing, and whether you're building a personal workstation or using cloud resources. Key factors to consider include CUDA cores, where more generally means more parallel processing power. Memory or VRAM is crucial, as larger models and larger batch sizes require more of it, and it's often a limiting factor. Memory bandwidth is also important, as higher bandwidth allows faster data transfer. Tensor cores, found on some NVIDIA GPU, accelerate matrix multiplications, which are common in deep learning. Of course, price is a major consideration, as GPU can range significantly in cost. Lastly, power consumption and cooling are important, as high-performance GPU consume a lot of power and require adequate cooling. Some popular GPU options currently include entry-level to mid-range options like the NVIDIA RTX 3060, 3070, 4060, and 4070, which are good for getting started. High-end consumer GPS like the RTX 3080, 3090, 4080, and 4090 offer significant performance, with the 3090 and 4090 being notable for their large VRAM. For professional and data center use, there are options like the NVIDIA A100 and H100, designed for large-scale training but at a very high cost. This visualization provides a hypothetical comparison of some key specifications for different GPU, including VRAM, CUDA cores, and tensor cores. The bar plots show how these specs vary across a few example GPU, helping illustrate the differences. In summary, this notebook provided lecture notes on setting up a deep learning workstation. We explored the benefits of using Jupyter notebooks for interactive development and documentation, discussed getting Keras running with the recommended tf.keras approach, examined the pros and cons of running deep learning jobs in the cloud, and analyzed the key factors for choosing a GPU for deep learning. Choosing the right tools and hardware is essential for an effective deep learning environment. Jupyter notebooks offer a powerful platform, and understanding cloud computing and GPU selection is crucial for scaling your deep learning efforts and optimizing both performance and cost. Thank you for joining this lecture.